Hello, everybody, and welcome to today's webinar presentation, Adopting a Microservices Architecture, Don't Forget the Data Layer, brought to you by Redis Labs. Before we get started, I have a few housekeeping items that I need to go over. First, if you have any questions for our presenters today, post those into the questions panel so we can get to them after the presentation. If you have any technical difficulties today, please post a message into the chat panel and I will work with you to resolve those issues. Last on my housekeeping list, today's presentation is being recorded. It will be available shortly after the webinar ends. And with that, I would like to hand over to Cheryl.
Thanks, Drew. Good morning, good evening, wherever you are. Thanks for being here. I'm Cheryl Sage, Director of Partner Marketing at Redis Labs, and we have an interesting session for you today on Redis and a microservices architecture. We'll hear from Alex Terletto, our Senior Director of Global Solutions at Redis Labs, and Paul Kermes, Director of Strategic Product Development at Mutualink. Welcome, gentlemen.
Good morning, good day.
Good morning, everyone.
So on tap today, our agenda is going to cover why the data layer is the first thing you should be thinking about when moving to a microservices architecture, how Redis can be used to scale your microservices architecture, and then we'll explore some popular microservice patterns using Redis Enterprise. And lastly, Paul will share how Mutualink uses Redis Enterprise to support his environment. So over the last couple of years, we've been seeing many Redis developers and customers moving to microservice architectures. In fact, this movement is backed by analysts predicting even greater acceleration in the next couple of years. With over 500 million apps that will be created in the next 2 years, 90% of these are going to feature microservices architectures, according to IDC. But moving to a microservices architecture has quite a bit of challenges. And in a recent survey that we did with Redis customers and developers, we found that developers are challenged with things like inter-service communication, data synchronization, latency between microservices, and service discovery. Operational challenges include things like monitoring and observability, orchestration, and some of the deployment complexity of many services. Now I'd like to turn this over to Alan, and he's going to spend some time getting into these data challenges in detail. So over to you, Alan.
Great. Thank you, Cheryl. Before we dive into the how and technology, it's important to begin by addressing the why. Why does it seem that everyone is either talking about, interested in, or already moving their architecture towards microservices? Where did all of this momentum come from? It's safe to say the willingness to move to smaller and more modular software has been around for quite a while. So why now? To answer this, sometimes it's helpful to take a step back and observe what else is changing around us. For example, our offices have changed from siloed cubicles to open space, changing the way we communicate with our colleagues. Our approach to project management has changed, moving us from traditional waterfall models to processes based on agile methodologies. The infrastructure we use has changed. Deploying software on virtualized environments is now the norm, with many organizations adopting clouds, running on virtual machines, or more recently, containers. Now, these transformations didn't happen overnight, and they did come at a cost. So the real question is, why are businesses investing? It's obviously a complicated answer, but if we had to boil it down, it comes down to time to market. As many companies have learned firsthand, when an industry becomes inescapably down this journey towards digital transformation, the competitive landscape changes rapidly. In some cases, the barriers to entry are reduced to the point where a startup with limited resources can disrupt an entire industry. In more common examples, competition is able to launch new digital products and services at rapid pace, no longer aligning to traditional release cycles. To make matters even more challenging, a new generation of technically savvy consumers are less loyal to brands and much more likely to move on to new products or digital services that are more personalized to their needs. Talk about a disruption to the business. So where do microservices fit into all this? Well, according to Conway's law, the structure of software will mirror the structure of the organization that built it. In other words, if an organization is siloed, our code is siloed. If our organizations have communication problems, our applications will have communication problems. However, it also means that if our businesses invest to transform these processes, their technology infrastructure, and overall organizational structure, you can bet they expect their software teams and software applications to mirror those transformations. So what's holding us back from delivering on all the promises of agile methodologies? Shouldn't just managing our projects using shorter sprints allow for more frequent deployments? Whatever happened to the promise of the 2-pizza rule? Shouldn't more smaller and more focused teams with better communication be able to operate with less distractions and therefore deliver quicker to market? We were told that lean processes and DevOps, all of those solutions were meant for the purpose of quicker time to market. Well, if organizational changes alone aren't enough, then certainly the dramatic changes in our infrastructure options must be the differentiator. We've seen a commoditization of infrastructure to the point where it's available on demand as a service through a cloud provider or on-prem as a PaaS. We can even take things to the next level by packaging together our operating system, platforms, applications, and configurations into a portable container and have it deployed, orchestrated across a cloud-native environment. Brilliant, right? But still, something is missing. We're still not getting to market fast enough. This is because we have yet to address the state of our software. Think about this. Does taking our monolithic application as is and packaging it within a container, orchestrating its deployment using Kubernetes in a cloud-native environment, would that actually improve time to market? Assuming that someone would even attempt this, I would bet the results were suboptimal. So maybe it's time to address the monolith itself and how we've even gotten to this point. Remember, Conway's law states that our software mirrors our organizational structure, which in most enterprises follows a traditional hierarchy with large departmental silos. Although these silos do have separate teams that potentially work on separate modules, they are all packaged and deployed as a single application, basically to align with the department or enterprise's release cycle. This is what fundamentally stifles time to market. Now, in a microservices architecture, we essentially decompose that monolith's modules and we break them off into fine-grained, independently deployable services so they can operate on their own release cycles. It's this very basic principle, which is at the core of how microservices finally allow us to break through that final barrier towards our goal of improving time to market. So now that we have conceptually agreed on what a microservices aims to achieve, how do we define what it is from a technical perspective? Personally, for things like this, I like to check in with the experts to make sure my assumptions are correct. One of the well-known experts in this field is Martin Fowler, who has written extensively on microservices. He's an author, international speaker, a blogger, and a self-proclaimed loudmouth on all things enterprise architecture. My kind of guy. In one of his talks, Martin concedes that there really is no consensus on how to technically define a microservices. It's kind of different to different people. However, him and James Lewis gave it a shot. So let me just kind of read it to you and see if it makes sense. In short, the microservices architectural style is an approach to developing a single application as a suite of small services, each running its own process, communicating with a lightweight business. You know what? This is it's kind of too much too fast, right? Let's kind of boil it down. Let's take a different approach. But let's stick with Martin Fowler as our guide. Instead of focusing on a definition, let's instead use the characteristics that he observed and shared with us through his extensive experience with real-world microservices architectures. This should be a lot easier for us to consume. These include componentization, which we have already defined as independently deployable fine-grained services broken off of the monolith. Now, in order to qualify as a component, it will need to avoid all dependencies on other components within the architecture. This also means that in the truest sense of microservices architectures, that it cannot share a database with any other microservice. That's a big deal, which will have ramifications and create complications, which we will be covering throughout this webinar. Let me show you an example of what that looks like. What you're seeing on the right is a real-world microservices architecture. It was shown to us at one of our reference conferences a few years back by a director from eHarmony. If I could have you focus in on what's called the core services, essentially they're microservices, things like profiles and photos and matches, what you might notice that each individual microservice has its own dedicated database. That's what we talk about when we talk about a component. Now, there's a lot more to this, and we'll get back to it, but let's focus on the characteristics. The second characteristic states that we have to organize around business capabilities. And this is basically saying that around our components, where do we draw the lines? Now, in the microservices world, the concept of being bound by a business context is a used term. And what that means is different to every other kind of business. To eHarmony, it means that we're going to bind these components to photos and matches. And then we'll provide the best possible database suited for those particular microservices and their SLAs. Going back to the characteristics, the concept of smart endpoints and dumb pipes. If you look at the reference architecture, you see a public API gateway, but that's essentially a pass-through to the different aggregation and microservices that are available. What you don't see is an ESB, an enterprise service bus. That came out of the SOA architecture world. The ESB was essentially the brain of the system. It would be responsible for routing between all the different SOA services available. Well, in the microservices world, it's all about isolation. The last thing we want is some other component that's aware of our microservice. All the intelligence belongs in the microservice itself. It is that smart endpoint, which means that everything else, all the lines between them, are just dumb pipes. It's just ways that we communicate between these microservices. We're going to go deeper on this. Next is decentralized governance and decentralized data management. And what that speaks to is empowerment. We're basically telling the teams, these small two-pizza teams, that they need to own these microservices. So we have to empower them if we want a great product to make their best decisions for that microservices. What's the most optimum database I need for my microservices? What's the right programming language for me to use? By allowing them to make those decisions, you're ultimately going to get a better product. So that's what speaks to about decentralization. The next is infrastructure automation. Now, we see this reference architecture with about 7 or 8 microservices, and that's always the way we think about it when we start things. But what about when it's 100, 200, 1,000 microservices? How can we possibly administrate and monitor and manage that type of environment? The only way to do that is with automation. The next one is design for failure. Now, again, let's take the example of 1,000 different components, isolated, right? In the old world with a monolith, we basically deployed everything as a single application. That means that when things were down, all things were down. Now, imagine you have 1,000 isolated components. Statistically speaking, it's very possible that 1 or 2 or more of those components at some point might be down. But we still have to be able to operate. So the mindset has to change. The mental model has to be adapted to design for failure. The assumption is at some point, something might not be down, but I still need to eventually communicate with it. This is where eventual consistency becomes at the core of a microservices architecture. Then we have the final 2 characteristics, products, not projects, and evolutionary design. Products, not projects, again, speaks to empowerment. Here, think about how we used to run things. We had a project. There would be a middleware team that worked on the project. There would be a database team, a UI team. They would basically work on some module and then walk away and work on a different project. Now we're basically saying that we need to treat every microservice like a product. You own it, you build it, but you also take it into production and you own it post-production. The only way for developers to do all of these wear all these different new hats and play these different new roles is to empower them to do so. So we'll talk about that. And finally, evolutionary design. Again, we talk about 1,000 potential microservices. Now think about your enterprise and the speed that it moves at. How long would it take you to realistically break up a monolith and get to 1,000 microservices? 2 years? 3 years? More? So if you are going to invest in this direction and think about the long term of the end state and when we actually get to a microservices architecture at scale, what are the things that are going to change in terms of the horizon of technology? Do we want to prepare for those changes? Do we want to think about the platform for the future as we implement the microservice of today? So we'll get into all of this. Now, we know the characteristics, right? We must be all good. Well, if you do enough Google searching on the topic, you'll find it's pretty busy. There's a bunch of new architectural patterns, new architectural concerns, a whole bunch of things to worry about. And a lot of them are focused on the data tier. That's not something we really dealt with as much in our monolithic architecture or even in SOA architecture, because essentially we worked off 1 or 2, maybe 3 databases. So how can we simplify all this? And how can we avoid having to develop all of this capability on our own? How does any of this connect back to what Martin Fowler taught us about the characteristics of microservices? And since I see Redis mentioned there on the right, where does that fit in? Before we can answer that question, let's make sure we're all on the same page first by quickly introducing Redis and Redis Enterprise. Redis Enterprise is an open source in-memory NoSQL database used for transactional, operational, and analytical workloads across thousands of enterprises. Its large and vibrant developer community has voted it most loved database 3 years in a row, and it's used in production across a wide variety of use cases. Redis is primarily a key value store, but is unique in its unmatched performance and its use of data structures, such as hashes, lists, and sets as core storage models. Redis Labs is the company that supports the open source community with webinars such as this, open source workshops around the world, full day events in major cities, with speakers from various enterprises sharing their experience like Paul, and even an annual conference called RedisCon. After many years of deploying Redis as a cloud service to its customers, Redis Labs decided to package their battle-tested knowledge of how to best deploy Redis as a database in a cloud-native environment into software that you can deploy on-prem, as a managed service, or even as a SaaS. This software is called Redis Enterprise. Redis Enterprise picks up right where Redis open source leaves off, with a full compliance to the open source API, including coverage of its data structures and operations, except for those that pertain to administration. That caveat exists because Redis Enterprise provides enterprise-grade administrative capabilities that are expected of a primary database, which includes linear scalability, high availability, backup and restore utility, security, and some unique capabilities such as multi-tenancy, active-active geo-replication, and tiered data storage. Speaking of unique, Redis Labs has extended open source Redis to allow Redis Enterprise to be a multi-model database. As you can see on the right, Redis Enterprise supports the native storage and query capabilities of models such as search, graph, time series, JSON, and more. Now, FYI, you don't need to worry about memorizing all of this. We will explore how each capability enables the simplification of deploying, administrating, and managing a database perfectly suited to a microservices architecture at scale. So let's finally jump into that. Now, we talked about the characteristics. They're not a free lunch. There's no unicorns here. There's no rainbows, as Cheryl mentioned. So let's address some of the challenges that these characteristics come with. So when we spoke about componentization, it was really all about isolation. And when you have all these isolated components in your architecture, you're really dealing with a distributed system. And we know a lot about that because Redis Enterprise is a distributed system. So you're dealing with linearization, eventual consistency, replication, the network. This is challenging stuff. So how does Redis at its core help us with isolation? Well, let's kind of build this up. Redis Enterprise, the instance of each Redis Enterprise is actually single-threaded. These instances can be run across a cluster in a multi-tenant way without having to worry about noisy neighbors. In other words, no connection between these isolated components. Redis Enterprise is a nothing shared architecture, so the individual nodes don't have to be in any way have dependencies. Redis Enterprise can run on virtual machines, containers, or cloud instances. Again, all isolated units of measure. It can even run on Docker. Redis Enterprise has integrations with all the major PaaS and IaaS vendors. So essentially what you're seeing is a platform that at every level of its stack is isolated. It's a perfect distributed system, which is perfect for the microservices world. That's just one less thing when you develop your distributed microservices architecture you need to worry about, because we already handled that concern out of the data tier. Now, when we speak about business context, how does Redis Enterprise help you design for these types of capabilities? Well, one of the unique things that we see, especially out of the open source community, is that a lot of services or capabilities or use cases that Redis is used for actually goes down to a single data structure. So what we see is if you're implementing a cache, you might just use the string data structure. If you're implementing a session store, you basically can use 3, 4 different operations on top of a hash data structure, and you're good to go. If you want to create a pretty strong and capable queuing system, you can actually just leverage lists. The same goes for sorted sets with weighted ordering type workloads, or market segmentation or personalization with sets, using streams for event source stores or event source message brokers. We'll get deeper into that. Or even having a microservice that's focused on geospatial capability by leveraging our geospatial indexing. So the simplicity of our data structures and the capability of them to drive an entire use case is perfect in the microservices world. Now, we talked about smart endpoints and dumb pipes. Well, those dumb pipes really speaks to the communication between all those smart endpoints. So where does Redis Enterprise play there? Well, we actually provide multiple message broker options. Whether you want to talk as a point-to-point queue, or whether you want to have publish to all of the subscribers, all the other microservices that are essentially talking to you based on some kind of event, or whether you want to leverage Redis streams as a replayable event engine and message broker that allows for pub sub, these are all options to you. And Paul's actually going to talk about the progress, the progress that they went through when they were choosing the right message broker for their microservices architecture. We'll get deeper into this when we get to the patterns. Now, the next characteristic is decentralized governance. This really speaks to, again, empowerment and choice for the developer. Now, if I want to deploy my microservices using Go or Python, or I'm an expert in Java or .NET, shouldn't I have that capability? But think about that as it applies to the data layer. Do I have to worry about, is my database interoperable with whatever programming language, and how do I communicate with my database? This is where the Redis open source community is a huge help. Our vibrant community has created hundreds of clients at this point across 60+ languages. That basically tells you that no matter what your developers are going to want to create their microservice in, Redis will be able to be interoperable with that particular language. It's pretty powerful stuff and empowering. Now, it goes beyond just the clients. Redis is so popular that almost all the third-party frameworks that I've seen integrate with Redis natively. So if you want to deploy a microservice as a Spring Boot application, go ahead and do so with no code, because Redis is already a part of the platform. If you want to create a reactive microservice, you could use React or Vertex Redis. If you want to create your microservice using Node.js, have at it. There's a Redis driver for that. Whether you're using Go or Kubernetes, anywhere you look, there's always going to be some integration with Redis. Now, what about decentralization of data management? This speaks to optimizing your database for the specific SLAs and needs of your microservice. Maybe you do need that referential integrity or relational database. Maybe you need the performance of a key value store and in-memory database like Redis. It really depends on and personalizes to the microservice, and your developers should have the choice. But what does that come from a challenge point of view? What is the challenge in that kind of mindset from an organizational point of view? We talked about 1,000 potential microservices. If we're choosing technology or databases and dealing with all the different vendors across the entire myriad of database options that are available to you, just because we want to optimize the model for that microservices, that is an organizational nightmare, especially on the vendor management side. So where does Redis Enterprise help? Redis Enterprise is a multi-model database. And what that means is you can essentially choose the most optimum model for your microservice running on top of Redis. So if the core data structures are not what you need and you're looking more for search capability or secondary indexing, have at it. Use Redis search. How about graph capability or time series? Maybe you're trying to serve some kind of tensor data. Maybe you need a JSON model. Now, instead of going out and getting a vendor just because you need to optimize your model, wouldn't it be better if you had a single database that can actually provide you all of the models and all of it in real time? That's the power of Redis Enterprise. And you can see what that looks like from a kind of a reference architecture perspective. Every database has its own, every microservice has its own database. Some need key value type performance, some need graph, some need search. Some might use Redis as a cache in front of the relational database, maybe a time series. But what you're seeing is you're optimizing the model and not having to get that additional technology in your stack. Now, infrastructure automation, always a pain, right? There's so many choices. And when we talk about empowerment, you kind of have to let your team pick out what they want to use, what's perfect for their particular stack. So where does Redis Enterprise help us there? Well, remember we were born on the cloud, so we are at our heart a cloud native technology. We actually provide a managed service for our Redis databases, and all of that is run through automation. And what we're doing is we're leveraging and we're exposing to our customers both the CLI, the Redis Labs CLI, as well as REST API. And that allows you and allows our customers to essentially integrate extremely easily with all these cloud native platforms and configuration management tools such as Chef and Puppet and Ansible, whether you want to run it on OpenShift or Kubernetes or Pivotal PCF. All of these can easily be tied together using the REST API in a very cloud native way, no matter how far you scale out. And we're optimized, because this is so popular, we want to highlight it, we're optimized for the Kubernetes deployments. We have our dedicated operator, leveraging stateful sets, automatic recovery, cluster recovery, rolling upgrades, rack zone awareness. We could do an entire webinar just on this alone, ability to deploy actively. But again, all of it meant to simplify the way you deploy and alleviate your concern about having to manage the database. We'll take care of that for you. Now, the next slide is about designing for failure, or the next characteristic rather, right? We talked about scaling to 1,000, some of them not being available, but you still have to meet all the kinds of SLAs, right? You still have to have fault tolerance in order to meet all the SLAs to your enterprise. So where does Redis Enterprise help? Redis Enterprise at every single level is fault tolerant. So we'll kind of walk through a few of them. At the process level, at the database level, at the database instance level, if we were to lose that particular process, you can see we will fail over to a replica on a different node seamlessly. That means that the client, which is sitting behind that proxy, will not have any impact. By the way, that proxy is actually a smart endpoint of its own, because underneath the hood, we are ourselves a microservices architecture. And what this means to you as a user is you don't have to worry about the server-side topology. You could do things like scale out automatically on demand, and there will be no impact to your clients. That means under load, there will be no disruption. Now, even at the node level, obviously we can handle fault tolerance. So if we were to lose an entire node, again, we're a nothing shared architecture, which we brought up a little earlier. And you could see that that proxy layer, it actually failed over. And then now we're using that secondary instance, and we still haven't really had disruption to our clients. Eventually that node will be recovered, we'll replicate back, and we'll be back into a healthy state with high availability. So we're able to handle that node failure. What if we lost a lot of nodes? What if we lost an entire availability zone? Well, Redis Enterprise actually allows you to run across multi-availability zones. So if you're running in the cloud, you can span a single database across multi-availability zones. Now, if you're on-prem, what that means to you is you can span multiple racks. If you were to lose an entire rack, we can actually have the fault tolerance to withstand that. Now, just me sharing my experience. If you're running in a virtualized environment, if you're running on VMs, always ask the question, are all of my VMs on separate servers? And then also ask the question, are those servers on separate racks? You might find out that in a lot of cases, they're actually not. So you do have a single point of failure. Even in a virtualized environment, it makes sense to have that rack zone redundancy, and you can leverage Redis Enterprise to have fault tolerance at that level. Now, let's say we lose the entire data center and we didn't have any kind of DR plan. With Redis being a database, we can actually persist, and we have the recovery options to allow you to get back to a healthy state. You can do that in two manners. You can do it as a snapshot, basically take the entire population of the database, or you can do that for each write as it comes, and you can persist it every second or for every single write. Now, we are a performance first database, which, as you can see on the left, means that we're going to respond to the client as fast as we can. It's always about sub-millisecond performance, and that secondary replica, it's going to be doing the persistence to the disk. Basically, the persistence will not impact performance. Now, this is tunable. If you have different kinds of SLAs and persistence needs, you can configure to use Redis database in a way that suits your particular needs. But let's say you don't want to have disasters. You don't want to have to recover. Your goal is to be always up. Now, not every microservice is going to need this, but there's probably going to be mission critical services that can't go down, right? Paul works in a mission critical line of work. So I imagine in his world, he's going to need that level of business continuity for the most critical services. So what we have here is our CRDB. It's really unique technology. because what it is it's actively replicating between these different databases that are geographically distributed across multiple regions, whether it's different data centers or different cloud regions. What's really unique about them is the way they manage conflict resolution. In other words, they do it for you. I work with other databases, and in their cases, they either use first right wins, or they basically delegate the responsibility of conflict resolution onto you, the developer. And that's a big challenge. Not only when things break down, but when things are working, but they're not actually working the right way. It's really hard to unravel that. We take a completely different approach. We based our CRDP technology based on a published paper out of MIT that used mathematical modeling to establish the most optimum way to do conflict resolution for each known data structure. Well, that's perfect for us because we're a data structure store. So we went ahead and implemented those concepts and took it to the next level, because for every single operation that we apply for that data structure, we actually publish how we will do conflict resolution to our customers. That means that our customers only need to review those policies, agree to them, and essentially never have to worry about this again. It's pretty powerful stuff, simplifying, especially when we're talking about the scale of 1,000 possible microservices. Now, how do we empower ownership, right? Products, not projects. It's all about data, right? So now if developers, we're talking about 2 pizza teams. That means essentially what that means is about 8 people. Now, if I'm on the team, that means about 5 people because I eat a whole pizza. I never really understood that 2 pizza thing. And kind of a fun-filled fact, I'll just add this in. The word micro actually speaks to the team size. Micro does not mean a small data set. And you sometimes hear people say it's a small amount of business logic. That's actually not accurate either. Micro speaks to the small size of the team that is needed to own this particular service. So how do we empower a group of developers who in the past just focused on development and then handed it off to administrators and UI and DevOps? Well, we provide the toolkit. So one of those is to have the data insights. So we provide Redis Insight, which, as you can see, is optimized for the data structures within Redis, as well as our Redis modules and specific nature of the data within Redis, such as search data, or time series data, or graph data. You can even do things like analyze memory. It's really powerful stuff and empowering to the developer. Now, on the administrative side, we really simplify things. We have a secure UI. Basically here, you can create databases, deploy databases with just a click of a button. You can scale things out in production, live. You can turn on high availability. All of this will be done behind that proxy layer as we talked about. It won't impact the client, and it's just a few clicks of a button. Very empowering to developers who are more used to the UI kind of driven world. And then there's the monitoring side. We integrate with Grafana. It's actually packaged with Redis Enterprise. We use Prometheus as a time series database to categorize all the metrics that are coming off of our system. And then we visualize it in Grafana, which is a very easily to use dashboard that developers can manage to see what's going on in production. Really empowering stuff. Now, we talked about the future, right? Being aware of the horizon and being ready for it. So what are the considerations as we potentially want to move in towards microservices? Well, we hope that we have the good problem of increased traffic volumes, right? We're creating digital products, and those digital products are bringing consumers to our websites and to our mobile apps. Well, that comes with the challenges on the data side in terms of throughput and latency. We want to be prepared for that increased volume. Luckily, Redis Enterprise was just recently benchmarked across 40 EC2 instances running 200 million operations per second. Now, you're probably never going to get there, but I hope you do. But what's really exciting about this is essentially means that no matter what level of scale from a throughput perspective you need to get to, you could be ensured that you're going to be able to do it all at sub-millisecond performance, because that's what we saw. You can see from 1 node to 40, we maintained that 5 million ops per second linearity. That's pretty powerful stuff. So you're prepared for the future. From a scaling point of view, you always hear in microservices world from the scale cube perspective. Now, I'm going to make it really simple. We don't want to get too deep into this. There's basically 3 axes. One is the x-axis, where we can just clone things for high availability. Well, we can do that with a monolith. We can decompose things to make it kind of separated. Well, you can kind of do that with a monolith, but you can't actually shard things. That's that z-axis. The monolith was not able to shard. That's where the old architectures fell short from a scaling perspective. Now, with Redis Enterprise, you don't need to worry about that. And you can scale every individual database that runs on our multi multi-tenant cluster individual to the needs of that particular database. Something you couldn't do in the old world, where everything had to scale together uniformly, whether it needed to or not. So here you can scale vertically to optimize the existing infrastructure you do have, eke out every single CPU that you need. Remember, we could tie down a Redis instance to a particular CPU to maximize that performance, or you can even share it if you wanted to. And then you can scale out horizontally across commoditized servers or virtual machines or cloud instances, whatever makes you happy. And then you can optimize that particular infrastructure and continue to rebalance and go forward. All of this can be done, as we mentioned earlier, dynamically without having to bring down your database or to impact your client. Powerful stuff. Now, how do I do all this and avoid increasing my operational expenditure to the point where it's not feasible? Well, Redis Enterprise, we mentioned, is a multi-tenant cluster. So you really are maximizing your infrastructure, reducing down your infrastructure spend. In addition, as we mentioned, micro does not mean small. There are databases that are going to potentially need a terabyte of data. So there is this inflection point that we've seen that after about 200 gigs, it starts to make sense to think about, do I really need everything in memory? Or can I get basically the same performance using Redis on Flash? And what Redis on Flash is, it uses tiered-based memory approach, where we're storing all the keys as indexes in memory, an LRU type cache for the hot values that are maybe 20% of your data set, where most of your action probably is, and then the rest of it on Flash, which is a much cheaper medium. And all of this is, again, completely seamless, and with a few clicks of a button can be set up. And what we've seen is basically 10x type of reductions in operational expenditure. I recently worked with a customer. They had about over a 1 terabyte deployment. It was going to cost them from an operational expenditure about $1 million a year to run all of that in memory. We were able to reduce it down to about $250K in terms of operational expenditure. So from a net OpEx perspective, they actually made money. So how do I know I'm investing in the right platform, right? Redis Enterprise sounds amazing based on what we discovered, but how do I know? And how do I, when I think about the future, make sure that I'm set up for success? Well, we're basically allowing you to future-proof your enterprise architecture because we're democratizing data across any way that you deploy on-prem, on any kind of PaaS environment, or on any one of the clouds. You can share that data actively through, with whether you're migrating to the cloud or whether you're using a hybrid cloud approach. Essentially, no matter where your enterprise will move to for the next 2 or 3 years down the road, you can be ensured that your data layer will not be a concern because Redis Enterprise is taking care of that for you. Now let's get into the microservice architectural patterns. We're trying to move quick. We're going to be just covering about 5 of them. Now, the most popular are CQRS. You've probably heard of this, asynchronous, publish and subscribe, sharing data, event sourcing, and we'll cover chain of responsibility. These are prevalent, and they come down to the data layer, so it's important to cover them. First, let's talk about shared data. You're saying to yourself, wait a minute, we talked about isolation. Well, if you look at the reference architecture provided by eHarmony, they're sharing data at that public API, which is okay. And it's very popular to use Redis as a session store or maybe user profiles, things that make sense for all these different microservices. So that is a popular pattern within the microservices world, and Redis plays into that. Now, a common anti-pattern, which you should be careful for, it might not bite you when you have 3 or 4 microservices, but it'll bite you for sure when you start to scale. And this comes from the mindset of smart endpoints and designing for failure. The distributed transaction, the 2-phase commit that we're used to, is an anti-pattern because you have to assume that a microservice will not be available, and you will essentially time out if you're creating a synchronous way to commit across multiple microservices. So it's an anti-pattern. But so how do we communicate, right? Fundamentally, the communication, those dumb pipes, really become a lot of the conversation around the microservices world. One way to communicate is asynchronous messages using a queue. So you can see here, we have an API gateway, we have 2 microservices, and what it's going to do is basically use a queue to communicate between the 2 microservices. Once I create my order, I can essentially put my event or my message onto the queue. My update inventory will be the only one listening for it, and it'll pick it up as it comes. Now, if that update inventory is not available, that's okay, because that queue is persistent. Now, if I had to operate on a more fire and forget model, if that made sense for my microservice, I can actually use Redis pub sub. So here you can see that I'm basically putting in a message, I'm publishing a message to the pub sub. It's completely transient, and it's posting that to all the subscribers on that particular pub sub channel. Now, I don't really promote this because it kind of goes against the characteristics of designing for failure, but this is something that's prevalent in the field. What is more interesting, I think, is using Redis streams as your event message broker. Now this goes to the event sourcing pattern. You hear about this a lot as well. Event sourcing comes down to fundamentally two components, right? We're going to really simplify things down. There's a message broker that is used to communicate, and then there's an event store, which is used as an immutable log for every single event that microservices processes. And this is for auditing, reconciliation, making sure that we didn't miss something, or even recovery, so we can make sure that we can recover to a certain state. So let's take this one piece at a time. We have an API gateway. We're using Redis streams as an event message broker. It's a lightweight communication mechanism, just as we noted earlier, just as Martin Fowler told us we need. And we're going to publish our event, or we're going to publish basically from the API gateway that we want to notify all the microservices that care about this particular message into Redis streams. Now Redis stream is pub sub, so what it's going to do is it's going to notify all the subscribers onto that message. Now you can notify them because maybe they're up and they're grabbing every message as it comes in real time, or maybe the other microservice was down. And what streams is different than the other published subscribe mechanism is, in this case, we're persisting that state. You're able to replay from any point in that stream or take things as they come. So really powerful stuff, especially in a world where things are supposed to fail. Now, once that message is within the microservices, what we'll do is we're going to log that to our immutable log. Maybe we'll have real-time reconciliation. Maybe we'll have real-time auditing. Maybe we'll have an arbiter pattern. But no matter what purpose we need for our event store, Redis streams is actually a perfect fit, because Redis streams, in its most fundamental purpose, is an immutable log. It's an append-only in-memory log, perfectly suited for an event store. Now, another popular pattern is the saga. A saga is a sequence of local transactions. Each service in a saga performs its own transaction and publishes an event. The other services listen to that event and perform the next local transaction. If one transaction fails, for some reason, the saga also executes compensating transactions to undo the impact of the preceding transaction. Now, there's two types. There's orchestration-based saga and there's choreography. In the orchestration, there's basically an orchestrator, a saga manager. Now, I don't really like this approach personally, because we are including this different component that is a smart endpoint. And that kind of goes against that principle. So the one we're going to be showing you here is the choreography. In this approach, there's no central orchestrator. Each service participating in the saga performs their transaction and publishes an event. The other services act upon those events and perform their transactions. In this example, we're building a state machine or an event-driven workload, which is referred to as a chain of responsibility pattern. This is what you would use if you have a dependency on writes between isolated microservices bound by different business contexts. So let's look at what that looks like. We're basically starting a workflow. It's creating an order. Create order is emitting an event saying, I'm done and I created my order. That's picked up by the inventory service, which is saying, I updated my inventory. That's picked up by the fulfillment service, and it's saying, hey, I did my fulfillment. Go ahead and do whatever it is that you guys do with now that we're ready to fulfill. Sorry, we're a little bit on delay here. Hope that made sense. Okay, so now we have the CQRS pattern. In the CQRS pattern, it's all about optimizing the write side and the read side of the architecture. We're separating those concerns. Think about it. If we're creating a database that's optimal for writes, is it really going to be optimal for reads? In most cases, not. So what we have in the CQRS pattern is the ability to separate those things. That's why it's called command query responsibility segregation. We're separating the responsibility for command, which is the writes, and the query, which is the reads. Now, what does that look like from a Redis enterprise perspective? We're passing in a message. It's being processed by the create order. That create order is published into a stream, and then the stream is notifying that, hey, I can actually move now that write to you guys, and you can optimize it for your particular model. Now, as you can see in the Redis enterprise world, you can optimize that model for the specific data access that's optimized, like search or JSON. You don't have to be using the same exact model that was on the right side. The whole point is to optimize for that data access. Now, you don't have to use streams for that. Another very popular way to do CQRS is actually leverage change data capture technology. This is more popular for when the source and the target are actually heterogeneous. In other words, they're different kinds of databases. Now, if I have a relational database on my command side and I go ahead and post to that, I can very seamlessly pick up that change and move it to one or more targets, which in our case is going to be Redis, And I could do that because Redis actually provides a change data capture technology. We're not going to be covering that in depth today, but we will be following up soon and more information about this. So we've covered so much ground here, the business level, the architectural concerns, and even some patterns that all relate to the data layer. But let's hear from someone that actually did this in a live production environment. We're lucky enough to have Paul Kermis on with us. Paul, would you like to take it from us and show us what you did in your journey with Redis Enterprise and microservices?
That'd be great. Thank you, Alan. So welcome, everybody. Let me introduce Mutualink to you. Mutualink's mission is to facilitate collaboration between federal, state, and local agencies and private entities to resolve dangerous incidents. Our systems provide situational awareness for first responders. We provide audio, video, and text communication so that all participants have a common vision and a common understanding of the environment. We should support sharing of arbitrary data like floor plans and pictures to enhance that view. We provide location sharing so that all the participants have a vision of where all of the other participants are at the scene. We support events large and small. Our tools let clients respond to everyday events such as traffic accidents and to spectacular events like the Super Bowl. We support local scope to support local agencies dealing with incidents like active shooter incidents at schools. And we have nationwide scope so that organizations can respond to threats over a large area, like a hurricane going up the coast. Our solution is called IRAP, the Interoperable Response and Preparedness Platform. It's our solution to provide multimedia sharing. A large part of that response is interconnecting application-specific devices like two-way radios and video distribution systems into a secure network to support the incident response. But more and more, our users demand access to this solution anywhere, anytime through smartphones, mobile-enabled laptops, and web clients. The scale is large, high reliability and high availability are key, and our response times, our latency must be low. So to address this evolving large-scale solution, we adopted a microservices architecture, and we depend upon Redis Enterprise. Redis is the primary data store for all of our microservices. It's the go-to source for information on the people and the devices who participate in our network. Redis is a key participant in the distribution of media to our clients, acting as a content cache, for text messaging and for buffered audio to be retrieved by clients after receiving push notifications. Redis maintains location information, and that allows us to provide maps to our peers. It helps us maintain secure control by supporting our authentication and authorization policies. And internally, we use Redis as a simple message queuing system. Now, since our product has national scale, high availability, and low latency demands, it's not sufficient for us to operate from a single network location. Our success depends upon coordinating services across multiple locations with consistent data. The Redis active-active functionality that Alan introduced is key for us. We gained that functionality with minimal design overhead to our product. The result is any request from any client can be delivered to any Mutualink network node in the country, and Redis will ensure that our data model remains consistent. And here we have a simplified overview of our microservices architecture, or at least part of that architecture. And much in the same pattern that Alan described, our clients have a single point of contact through the customer services block. Once that block performs authentication and authorization confirmation, operations are delegated to a single internal service that satisfies that business request. The world service has the special responsibility of maintaining the overall network model, and generally speaking, that's a retrieve-only function for the clients. The collaboration service maintains the communications model. Who's participating in an incident response, what audio and video and text messages have been sent, what files are shared. And the collaboration service is really the central actor from a command perspective. We have other services that support maintenance of that location and presence information, and an event distributor that maintains a internal web for one-to-many subscription to deliver messages to other core services and to other services that aren't shown in this diagram. Virtually every service depends upon Redis in some way, and typically that's the specialized database underlying each specific service. Redis is critical there because without an efficient data store that's targeted to a particular microservice, it's just not feasible to implement that stateless microservice architecture. So now I'll get a little geeky and provide a bit of detail about aspects of our design process. The goal of the microservice architecture is to satisfy business requirements, and each microservice instance is just one of a herd. There may be uncountably many instances executing at one time. We need that scale because there's hundreds or thousands of clients simultaneously requesting services. Now, one of the core functions of our system is to establish those multimedia communication collaborations. Every collaboration's got a set of members and a set of media, but there's no central controller. Any member can change the membership or add media or remove media at any time. That means requests can collide in our data model in the representation of the collaboration, but every one of the requests must succeed and the model must remain consistent. So we learned quickly that there was no single Redis data type that represented the software model that we would implement in typical programming languages. So our model depends upon a combination of Redis data types and techniques. And just hitting some of the highlights, we use hashes to represent structures. Each field in the hash represents a data member of a structure, and we can add new fields to the hash. There is no hard schema to deal with. We represent each object's association with other objects using a set of related object keys. And then that key that represents that collection is typically derived from the key of the structure just using string manipulations. So for example, if we had some object type and ID as the collaboration structure, his relationship of members might be called assoc: members: collaboration: ID. And that's a really common Redis pattern that we found, and it was very powerful for us. For performance, we knew we needed to handle those colliding requests by limiting the nexus of the collision. And as we modeled out our solution, we confirmed that our collisions would primarily occur in the set, maintaining those collections. And we found that this was a really effective model for our particular problem. Now, for the actual execution performance and maintaining data consistency, we lean on two key Redis patterns. First is called pipelining. It's necessary for an efficient microservice to bunch together many operations on the data model into a single burst to eliminate stop and wait actions on the Redis system. But for consistency, we have to use Redis's transactional model, which depends upon operations in the Redis API called multi and exec. With that pattern, we're able to group together the operations on multiple objects and commit them into the Redis store as if they're a single atomic operation. And that model succeeds even as we grow the size of our Redis deployment across more nodes and more shards, and we ensure consistent data locally. Now, our use of the active-active capabilities does add a bit of complexity because clients can be communicating with multiple network nodes and modifying our data model simultaneously. But as Alan said, the conflict resolution rules for each type are documented. So we just held up our data model against those conflict resolution rules to ensure that we would have consistent behavior across all of the data centers. And the good news was the data model we conceived for the single site solution required no changes to gain the proper behavior across our active-active deployment. Internally, some of our microservices perform delegation operations using REST calls, HTTP calls inside of the box. But in many cases, we've found that leveraging Redis as a simple message queuing system was more efficient. It allowed us to have an application-driven work assignment strategy rather than depending upon a load balancer distributing requests as connections are opened. The list structure we found gave us more elasticity to a large work queue of requests than we'd ever gain from a socket-based HTTP model. And because all of the microservices maintain active client connections with the Redis server, we're able to avoid startup and teardown costs of the sessions. But we are working on a transition to an even better solution, as Alan described, the stream. Streams have a much more complete lifecycle model, and what we're focusing on is the high reliability. Our understanding is that we'll be able to represent the lifestyle of a request, the lifecycle, not lifestyle, of a request. And if an instance of the microservice failed during the processing of an operation, other instances can come back, pick up the work, complete the work, and all of the work gets done with a good record of the operations. Certainly, we've got other message queuing solutions available. There's a wide availability of packages that are used, but Redis does enough to solve our problems. We don't incur added cost. No additional software licensing, no additional software components to maintain, and no new APIs for the team to learn. Now, not all of our applications problems are solved by Redis's built-in data types, but the multi-model database supported by Redis modules addresses gaps by creating new data types and operations that we can depend upon. For our application, Redis Search is a critical tool. Redis Search implements indices over many different data types and gives us efficient searching and sorting and manipulation of referenced objects. And we use that for two key problems in our application. Our first case is text matching over a directory tree. We give our clients a hierarchical representation of their peers, similar to a file manager view on a computer desktop. Now, if the user knows the name of a partner or part of a name of a partner agency, but doesn't know where that partner is located in the search tree, we need a search method, and Redis Search gives us that. We can build an index over the entire tree, and the user can simply type in what he knows, a few characters or a whole word, and we can perform a set of searches across that entire index and give the user suggestions of who matches what he entered. From that, the customer can refine his request or pick exactly who he's looking for. Now, the business value for this, whether it's the initial setup of a favorites list or an urgent need to find a peer during the incident response, we believe Redis Search accelerates our users' ability to navigate that large and growing directory, and that's going to improve customer satisfaction. And then the other key Redis Search case is our geographic data display. Our clients can display maps showing the location of other clients, whether they're participating in an active incident response or if they're just looking to see who's available in the vicinity to bring into that response. Now, that data is built from location reports that come from each client application, and those reports might be made multiple times a second, depending upon the client's movement and the particular settings of the device. So we have to handle a large number of location updates coming into the system, and then we need to be able to efficiently search that database to provide the map that the customer is looking for. And that's an expensive search for an application program if you don't have a specialized index in place. But Redis Search has that geospatial index. So we're able to satisfy the request for matching peers in a single request to the Redis store. The direct benefit to our customers is the quick presentation of that data. Knowing the location of responders during an incident response is key, because if the commander doesn't know where his team members are located, he can't effectively direct the operation. And you can visualize how important that is during a response to a school shooting. We anticipate using another Redis module, the time series, to solve the problem of application monitoring. We know that without quality statistics from the application, we won't be able to track the number of requests being processed, the time it takes to process each request, or how much bandwidth is being consumed by a particular media stream. But in my experience, performance monitoring is an afterthought in many software projects. Since it doesn't generate direct revenue, it's an easy project to delay when the schedule is tight. And what's more, to create a solution requires a full stack effort. You have to collect, store, retrieve, interpret, and present data. But our understanding now is that this doesn't have to be the developer's responsibility. We can depend upon an infrastructure that's already available to us through time series. So the time series data type is specialized for collecting samples of data over time with memory and performance efficiency. So now we can simply add in the setting or incrementing of values into an appropriately keyed time series object in the Redis store. And based on the configuration of that object, Redis will automatically aggregate metrics over time and purge unnecessary detail. So that solves the collection and storage problem. They're still retrieving, interpreting, and presenting. But as Alan said, time series is integrated with well-known tools like Prometheus and Grafana and others. So those tools already know how to extract the time series data from Redis. We simply need to work with our team to define the appropriate keys and then add that information to the monitoring dashboard. Now that doesn't have a direct benefit for our customers, but it has a direct benefit for our operations team because we ensure consistent management of our system. We'll know when we need to increase the scale of our deployment, but more importantly, we'll also know that we're not over deploying the system and we can control our costs. So in conclusion, for Mutualink, our partnership with Redis Labs has been an incredible benefit. We've been able to converge on effective data models for the microservices architecture very quickly using the training material available on the web and with supports from experts like Alan within the company. I anticipated spending many staff years creating a functional active-active synchronization solution, but we were able to leverage that functionality out of the Redis Enterprise distribution for an immediate solution. And as additional problems have presented themselves, we found the tools that we need in Redis and in the modules that are available. Thanks for your time and interest today. And Cheryl, back to you for questions.
Yeah, great. Thanks so much, Paul. That was so informative. We actually have run out of time today, so we're going to have to cut the Q&A session. I want to thank everyone for attending. And thank you, Alan and Paul, very informative sessions. We have a Redis microservices ebook for developers. You can check that out online to get more information on implementing Redis and a microservices architecture. Back to you, Drew.
With that, I would like to thank Cheryl, Alan, and Paul for a great presentation. I would also like to thank Redis Labs for providing the audience with a great webinar. Lastly, thank you to everyone who attended. We hope you learned something new that will help you in your developer career. Have a great day.